This is a video in clinical medicine from the New England Journal of Medicine.
Disposable pressure transducers are ubiquitous in the modern hospital. Physicians should understand how the transducers work and how to interpret the data they provide. This video will review the use of a pressure transducer to monitor hemodynamic pressures in adults. The video will not provide expansive descriptions of the applications that are presented, and it will not cover every possible use of the pressure transducer. The use of a pressure transducer is indicated when continuous and precise measurements of clinical hemodynamic pressures must be obtained. For example, a pressure transducer can be used to monitor intra-arterial pressure when the measurements obtained with a non-invasive blood pressure cuff would be too infrequent, or it can be used to monitor central venous pressure when the results of physical examination would be too imprecise, or when following trends is deemed useful. This animation presents a simplified version of how pressure transducers work. The inside of the pressure transducer contains an impermeable silicone diaphragm. One side of the diaphragm is in contact with the fluid in the pressure tubing, and the other side is open to atmospheric pressure. The pressure of the fluid physically deforms the diaphragm. Through these small changes in shape, the diaphragm stretches or compresses strain gauges that are attached to it and consequently changes the electrical resistance of the strain gauges. These changes in resistance are subjected to mathematical transformation within the monitoring software and displayed as a waveform. The circuit is pre-calibrated so that its output voltage maintains a linear relationship to changes in pressure. Consequently, an individual transducer does not need multiple points of calibration. Rather, it needs to be zeroed to a single reference point. According to clinical convention, the zero point is defined as the pressure in the transducer when the diaphragm of the transducer is level with the patient's right atrium. The items used to set up a pressure transducer include a transducer kit with a fluid line, a bag of fluid that may or may not contain heparin, depending on the guidelines at your institution, an IV or intravenous ball, a mounting plate, a pressure infusion bag, and a monitor with a cable to connect the transducer. Some transducer kits contain a single transducer, whereas others contain 2 or 3 transducers. A single fluid source and pressure bag may supply all units simultaneously. The design of the transducer flush valve may vary, but the purpose is the same. The 2 most common designs are a flush valve with a pigtail which is pulled to flush the tubing, and a flush valve with 2 plastic wings that are squeezed to flush the tubing. The transducer used in this video is equipped with a pigtail. Specialized transducers, such as those used to monitor hemodynamic pressures in neonates or to monitor intracranial pressure, will not be discussed. This demonstration will show you how to set up a transducer for hemodynamic monitoring in an adult. To begin, make sure that all tubing connections are tight. Then slide the transducer into the mounting plate. Open and spike a bag of normal saline, which may or may not contain heparin. Open the flush valve by pulling on the pigtail, and squeeze the bag until all the air has been expelled and the drip chamber is half full. Place the fluid bag inside a pressure infuser and hang it from an IV pole. Turn the stopcock 90 degrees toward the patient's end of the tubing to open the vent port, and allow fluid to run through until all the air bubbles have been purged. Close the vent port and open the flush valve by pulling on the pigtail until the remaining tubing is filled with fluid. The pressure infuser should now be inflated to approximately 300 millimeters of mercury. This pressure ensures a slow, continuous flow of fluid, approximately 3 cc per hour, and prevents the backflow of blood into the transducer system. Check the transducer once again by tapping the transducer and tubing while flushing, to make sure that all air has been purged from the system. The system can now be connected to the monitor and calibrated. The transducer should be placed at the level of the structure of greatest interest. For instance, when cerebral perfusion pressure is monitored, the transducer should be level with the circle of Willis. Most hemodynamic measurements are made relative to the level of the patient's right atrium, which corresponds to the fourth intercostal space at the mid-axillary line when the patient is lying in the supine position. Slide the mounting plate up or down the IV pole until the transducer is at the level of the patient's right atrium. A water level can be used as shown here. While zeroing the system, make sure the stopcock is turned toward the patient's end of the tubing so that the vent port is open and the transducer is exposed to atmospheric pressure. The cap on the vent port may be fenestrated to allow exposure to atmospheric pressure. If the cap is not fenestrated, it must be temporarily removed. Activate the zeroing function on the monitor to complete the calibration of the transducer. When the calibration has been successfully completed, the transducer tracing will be at baseline and a pressure of 0 will be displayed. Turn the stopcock back to the middle position to close the vent port and replace the cap if necessary. The transducer system and monitor are now connected, calibrated, and ready to be connected to the patient's cannula for monitoring. All other electrical properties of the transducer were calibrated by the manufacturer and do not need to be readjusted before use. When analyzing a pressure waveform, always make sure that the transducer has been zeroed and leveled, and select an appropriate scale on the monitor. When the scale is made larger, the waveform appears smaller. Conversely, when the scale is smaller, the waveform appears larger. Inspect the waveform quality to assess for possible overdamping or oscillations caused by underdamping. Compare the pressure tracing with the plethysmographic waveform obtained from the pulse oximeter and with the electrocardiogram to rule out the possibility of artifacts. There are many problems that may cause inaccurate pressure measurements. The most common are improper setup and malfunctioning of the transducer system. If no pressure tracing is displayed, potential causes include clotting in or dislodgement of the cannula, kinking of the cannula, disconnection of the cable, improper scaling of the waveform, and transducer failure. Try aspirating the catheter from the stopcock with a syringe. If there is no blood return, the cannula may be occluded or may have become dislodged and may need to be replaced. If there is blood return, check the electrical and fluid connections of the transducer system and verify that the scale of the monitor has been set appropriately. If the transducer fails, for instance, the transducer cannot be zeroed or does not produce any data, a new transducer system should be calibrated and connected to the patient's cannula. If the pressure waveform appears to be overdamped, common causes include low blood pressure or a lack of fluid in the infusion bag, an air bubble or small clot in the system, kinking or obstruction in the intravascular catheter, loose or open connections, or improper scaling of the monitor. Make sure the infusion bag is inflated to a pressure of 300 millimeters of mercury. Check for loose connections and ensure that the intravascular catheter is patent and free of clots and air bubbles by aspirating and flushing the line. Check the monitor to make sure that the proper scale is in use. If the pressure waveform is underdamped, common causes include movement of the cannula in the blood vessel, excessively stiff tubing, or a defective transducer. Make sure that the correct tubing is being used. Pressure monitoring tubing is less compliant than regular intravenous tubing, which is more flexible and interferes with dynamic response. When the pressure waveform is erratic and pressure readings are highly variable, it is likely that excessive motion of the catheter in the vessel is causing the pressure reading to oscillate around its true value. This condition is known as whip or flail. Consider repositioning the catheter or changing the cannulation site. The most frequent complications associated with the use of a pressure transducer can be attributed to misuse of the equipment and misinterpretation of the data. If the patient is lowered, then the patient's blood pressure will appear to fall unless the transducer is reset at the level of the right atrium. If the patient is raised, the patient's blood pressure will appear to increase until, again, the transducer is level with the patient. Similarly, if the transducer falls out of the mounting plate so that it is situated below the patient, the blood pressure will appear to increase dramatically. For every 10 centimeters of mismatch between the level of the patient's right atrium and the level of the transducer, the blood pressure measurement will be in error by approximately 7.5 millimeters of mercury or 10 centimeters of water. The blood pressure measurement is not affected by the level of the insertion point in the vessel as long as the transducer is maintained at the level of the patient's right atrium. In order for hemodynamic measurements to be accurate, be sure that the system is correctly calibrated and zeroed. Before you begin aggressive treatment for hypotension or hypertension, check again to be sure that the level of the transducer is correct and that the measurements are accurate. Complications can also occur if the transducer tubing becomes disconnected or if a stopcock is left open. If the transducer system is connected to a central venous catheter, then the patient is at risk for either hemorrhage or venous air embolism, depending on the position of the catheter relative to the heart and the central venous pressure. If the transducer system is connected to an arterial cannula, then the patient may rapidly become exsanguinated. It is therefore essential to ensure that all tubing connections are secure and that stopcocks are placed in visible locations. Pressure transducers that are connected to an arterial cannula pose additional risks. The risk of accidental intraarterial administration of an intravenous medication is greatly increased. Also, any contamination or air in the line can be inadvertently flushed directly into the arterial circulation. A rapid flush or injection can create a brief retrograde flow in the arterial tree that could allow emboli to travel to the cerebral circulation. Carefully removing air from the infusion bag and transducer system minimizes the risk of air embolism. Finally, the use of an indwelling catheter increases the risk of infection, and pressure transducers have been associated with the transmission of bacterial pathogens. Transducers must be discarded according to infection control guidelines. Pressure transducers are an important tool in the care of critically ill patients and are used during a variety of specialized procedures. Clinicians should be familiar with the indications for their use, understand how they work, and be aware of the associated complications. When pressure transducers are used properly, they are a safe and valuable tool.